Hey everyone, let's jump right into this explainer. We're looking at a concept today that, honestly, trips up even seasoned engineers. Restricted Earth Fault Protection, or REF. We're going to see why two totally different schemes share the exact same name. And more importantly, how mixing them up means your commissioning checklist is going to be wrong from day one.
Here's the wild part. You can have two schemes, both called REF, that look nothing alike out in the field. One needs zero extra hardware, just the relay itself crunching numbers. The other? It needs a physical, stabilizing resistor bolted to a panel, maybe a varistor, and perfectly identical current transformers everywhere. Get them confused, and you are in for a massive headache.
So, to make sure we get this right, here's our roadmap. We're going to define the invisible security fence, compare our low and high impedance options, lock down the CT matching rule, bust a pretty common high impedance myth, and finally, figure out how to select the right hardware.
All right, Section 1. The invisible security fence.
Let's talk about what reef protection is actually doing electrically. Think of it like drawing an invisible security fence right around the transformer winding and its neutral connection. Any fault current inside that fence, the relay trips. Anything outside? Ignored. We need this because standard overcurrent protection has a really hard time telling the difference between a tiny internal ground fault near the neutral point and just massive current flowing through during an external fault. We absolutely need that true selectivity.
To picture this in action, think about configuration A on the high voltage side. The relay is taking inputs from both the phase CTs and the neutral CTs. It's basically acting like a magnifying glass, zooming in specifically on that neutral point, because that is exactly where a small fault is most likely to hide from your broader protections.
Moving on to Section 2, low versus high impedance. Okay, so let's break down the two ways we build that invisible fence, starting with low impedance ref. This is your flexible, software-driven option. You don't need any extra hardware for this to work. It just uses numerical algorithms right inside the relay to handle mismatch current. Because it handles everything in software, it's completely fine if your phase CTs and your neutral earthing CT have totally different turns ratios.
On the flip side, we have high impedance ref. This is the old-school traditional hardware approach. During an external fault, instead of using software, it forces mismatch current through a physical stabilizing resistor, which can be anywhere from hundreds to thousands of ohms, keeping it away from the relay coil. You trade that software flexibility for rock-solid stability. But, and this is a huge but, it demands absolutely identical CT turns ratios across the board, no exceptions.
Which brings us nicely to Section 3, the CT matching rule. This is the unbreakable engineering rule that makes your decision for you. Mismatched CTs completely require low impedance ref. Let's say you're doing a brownfield retrofit. Your phase CTs are 2000/1, but your old legacy neutral CT is 1000/1. Guess what? You are automatically locked into the low impedance scheme. High impedance is off the table right then and there.
I like to think of low impedance reef as an adjustable combination lock. You can reprogram the software to fit almost any door, or in our case, any weird set of mismatched CTs you happen to inherit. High impedance reef, though, that's a fixed key deadbolt. It only works on one exact lock. Sure, it's way less flexible, but for that one specific door, literally nothing beats how secure and stable it is.
Okay, Section 4, the high impedance myth.
We've got to clear up a misconception that causes so many commissioning delays. A lot of engineers assume that because high impedance REF is the traditional ultra-stable method, it's just automatically the superior choice every time. So, true or false? Is high impedance always the way to go for the best protection?
That is a hard false. If you're working on a retrofit with legacy CTs of unknown or mismatched ratios, low impedance isn't some second-rate compromise. It's literally the only workable option. If you try to force a high impedance setup onto mismatched CTs just to, see if it works, that uncompensated mismatch current has absolutely nowhere to go except right through the relay coil. You're just asking for a false trip or completely damaged components.
Now that being said, if your CTs do match perfectly, configuration G for the high voltage side is a great example of this done right. When you implement it correctly, that extra stabilizing resistor gives you extreme sensitivity for faults really close to the neutral point. That raw sensitivity is exactly why it remains such a highly respected utility standard today.
Let's wrap this up with Section 5, selecting the right configuration. So how does this translate to ordering your actual hardware? Your configuration letter is strictly mapped to your network. Configurations A, B, E, and F, those are your numerical low-impedance setups. C, D, G, and H are your high-impedance setups. Your choice entirely depends on if you're protecting the high or low voltage side, and most importantly, whether your CTs are forcing you into that low-impedance bucket.
Your default decision path should literally always look like this. Step 1. Check those CT turns ratios. Always. If they're mismatched, you go to Step 2, which means you instantly select a low-impedance configuration. Boom. Half your options are eliminated, no debate needed. Only if those ratios match perfectly do you proceed to Step 3, where you finally get the luxury of choosing between software flexibility and hardware stability.
If you take one thing away from this explainer, let it be this. Your physical network parameters dictate your protection strategy, not just your personal preferences. You can't just pick a configuration because it's what you're used to. The physical realities of the site, like your earthing and your CTs, are in the driver's seat.
And that leads us to a really interesting question for our next explainer. If your CT ratios dictate your entire protection scheme like we just saw, what happens if those foundational measurements are completely misconfigured? If your CT settings act like a universal translator for all the relay's logic, what actually happens to your downstream redundancy when the relay gets the wrong translation? We're going to tackle that exact nightmare scenario next time. Thanks for hanging out with me on this deep dive. I'll catch you in the next one.